Derneği 6. Tosun Terzioğlu konuşması. Girişi Türkçe yapayım, sonra matematikle ilgili her şey İngilizce olacak zaten. Biliyorsunuz Tosun hocamızı 2016 yılında kaybettik. O sırada dernek başkanı olan Betül Tambay hemen bu Tosun Terzioğlu konuşmaları serisini başlattı. Ve o günden bugüne kadar yıllık olarak düzenlenmekte. Tosun hocamız 19 yıl boyunca dernek başkanlığı yaptı. Ve sadece dernek başkanlığı değil, yönetim kurulunda çeşitli görevler de aldı. Hatta ayrıldıktan sonra bile hala projeleriyle, fikirleriyle, görüşleriyle derneğe destek olmaya devam etti. Gerçekten dernek için çok çok kıymetli bir isim. Üstelik bugün şöyle bir hayat hikayesine tekrar bakarken fark ettim. Bu 19 yılın hemen hemen yarısında Ankara'daymış. Hem ODTÜ'de öğretim üyesi olarak hem de TÜBİTAK başkanı olarak. Ona rağmen dernek başkanlığını yürütmüş. İkinci yarısında da Sabancı Üniversitesi'nin kurucu rektörlüğünü yapmış. Yani gerçekten iki tane önemli işi ki yaptığı başka bir sürü iş daha var. Birlikte yürütüp bir de üst düzey araştırma yapabilen bir matematikçiydi aynı zamanda. Gerçekten hayran olmamak mümkün değil. Gelelim bugüne, bu yılki Tosun Terzioğlu konuşmacımız Özlem İmamoğlu. Özlem İmamoğlu is from ETH Zürih Üniversitesi. She got her first degree in electrical and electronical engineering in Middle East Technical University in Ankara. Then, in her master's and PhD studies, she switched to mathematics. She received her degrees from University of California, Santa Cruz. And then she took various posts in America or in various research centers she visited. And also she spent a year, one academic year in Sabancı University, 2000 and 2001, I believe. And finally she has been working in Zurich since, I forgot, 2002. And her research area is in number theory, more specifically on automorphic forms. And I vividly remember her mini course in anti-algebra in 2006. It has been a long time, but I still remember, on modular forms. It was a really good course, great course. Now we will listen from her the state of knowledge from class, about class numbers. Thanks for accepting our invitation.
Çok teşekkürler. Ben de başlamadan Tosun Bey ile ilgili belki bir iki şey söylemek istiyorum. Tosun Bey ile benim tanışmam ODTÜ Elektrik'te öğrenciyken 1984-85 yıllarına dayanıyor. O zamanlar geriye baktığımda şimdi cahil cesareti olarak gördüğüm mühendisliği bitirdikten sonra acaba matematikte doktora yapabilir miyim düşüncesiyle matematik bölümünden aldığım birkaç dersten birinde hocam oldu. Daha sonra da doktoraya başvururken benim için bir referans mektubu yazdı. Sonuç olarak doktora yapabilmemi büyük olasılıkla Tosun Bey'e borçluyum. Ondan yıllar sonra 2000 yılında Sabancı'ya tam kuruluş zamanlarında öğretim üyesi olarak geldiğimizde tekrar Tosun Bey ile bu sefer birlikte çalışabilme imkanına eriştim. Ve o zamanlardan kalan bir sevgim ve derin bir saygım var. Bunun nedeni de açıkçası her konuda anlaşmış olmamız değil. Tam tersine profesyonel olduğu sürece aynı fikirlerde olmasan da uyumlu ve mutlu bir çalışma ortamının sağlanabileceğini ve iyi bir yöneticinin farklı düşünceleri negatif bir öğne olmaktansa pozitif ve avantaja kullanılabilecek bir şey olduğunu göstermesi idi. Sözü daha fazla uzatmadan kendisiyle tanışmış olmak, öğrencisi, çalışanı, meslektaşı olmaktan büyük gurur duyduğum Tosun Terzioğlu konuşmalarını vermek benim için büyük bir onur. Teşekkür ediyorum. Konuşmanın scientific kısmını maalesef İngilizce veriyorum. Bu bir utanç kaynağı benim için. Fakat geriye baktığımda ortaokuldan başlayarak matematik derslerinin hepsini İngilizce öğrenmiş olmanın etkisiyle özür dileyerek İngilizce olarak scientific konuşmayı verir. Okay, the title is what is a class number and what do we know about it. I'm not going to assume anything that people are specialists in number theory. But the notion of class number actually is very old. It goes back to Gauss, and it appears first in the Discussiones in 1801. And in this work, Gauss laid the foundations of the theory of binary quadratic forms. These days, these are worded in terms of in the context of not quadratic forms, but quadratic fields. So let me first give a quick introduction of what the class number is. Two quadratic forms that we have. We start with two quadratic forms, ax squared bxy plus cy squared, and the second one with coefficients big A, B, and C. We call them equivalent if one can go from one to the other by a linear change of variables. I'll make this more precise. Then the class number is the number of equivalence classes for this equivalence relation once we fix the discrete. As I mentioned earlier, later everything about class number is phrased in terms of number fields and ideal class groups. And this is going back to Dedekind. It actually started with Kummer, who developed the theory of ideal numbers. It was really Dedekind that laid the modern foundation of number theory. As I said, between Kummer and Dedekind. And if you have heard the fundamental theorem of arithmetic, it says that every positive integer can be written uniquely as a product of prime numbers. And in one of the first courses in algebra, we see that this does not necessarily hold in arbitrary rings. And indeed, it became apparent that the failure is something that can be measured by a group, the so-called ideal class group. As I said, Dedekind is the one that introduced many of the things that we use today. In particular, he introduced the ring of integers of a given number field. The number field is a finite extension of the rational numbers. And he showed that every non-zero ideal has a finite index, and it can be factored uniquely as a product of prime ideals. So if you move from numbers to ideals, he showed that the unique factorization property holds. And he also introduced this famous zeta function, now we call the Dedekind zeta function, which is a sum over all ideals of the field K, 1 over norm of the ideal to the S. One has to show that it converges, but it converges for real part of s bigger than 1. And the norm of the ideal is defined as the index of the ideal in the ring OK. And if the field is the rationals, this boils down to the classical Riemann zeta function, which again converges for real part of s bigger than 1. And nowadays we know that both of these zeta functions has an analytic continuation and functional equation. Dedekind was not actually able to prove the functional equation. It waited until, I think, 1918, when Hecke finally proved the functional equation of the zeta function. So what is the ideal class group? To introduce that, we again define an equivalence relation on the ideals of the ring. And we call two ideals, A and B, equivalent if there are numbers in the ring of integers, alpha and beta, such that the principal ideal generated by alpha times A is equal to the principal ideal generated by beta times B. What is important to know that it is an equivalence relation on the set of all ideals of the ring. And then if you look at the ideals modulo this equivalence relation, so we are looking at the set of equivalence classes, then this forms an abelian group, the so-called ideal class. And it's a famous theorem of Minkowski that this group has finite order, which is not at all obvious. And it is for this purpose that Minkowski developed his now famous geometry of numbers theory that has applications to many other areas. And the order of this finite group is called the class number, and this is what I really want to talk about today. And it is known that the class number is 1 exactly when the ring of integers is a principal ideal domain. In the case of integers, for example, that is the case, the usual integers. Okay, so this is the general class number, but let me go back to the very simple case of quadratic forms and quadratic fields. And I'm going to use most of the time the language of quadratic forms because it is simpler, it requires less from us to know. So let's introduce the main players. For this, I want to define a relation on the quadratic forms, and for this I need a group, and the group will be the modular group, and it acts on the upper half space. These are the complex upper half plane, complex numbers with positive imaginary part. And the group SL2Z are the set of 2 by 2 matrices of determinant 1 with integer entries. And the modular group is this group modulo plus minus identity. And in complex analysis courses, we've seen that the group acts on upper half plane by linear fractional transformations. In fact, even the SL2R acts by linear fractional transformations, or sometimes called Möbius transformations. And whenever we have a group acting on a set, we can ask about the set of representatives of this action. In this case, it is actually an infinite set. It is the one on the left. So this purple shaded area is a set of representatives, and it's called a fundamental domain for this action. It is not unique, but this is the most standard one. It is bound by vertical lines, real part of x equals minus a half and a half, and about the unit semi-circle here. And then we can act, this is a fundamental domain, means that we can act on this set of points by the group, look at the translate, so we can translate them, we can what we call inversion, and that gives a beautiful tiling of the upper half plane, which is called the modular tile. You might have seen this picture. I have a colleague in the department who has a cupboard made with this shape. He really paid and in Switzerland, so he probably paid a lot to have this stuff. Who's a number theorist, needless to say, I guess. Okay, the second player is quadratic forms. We fix an integer, d, which has to be 0 or 1, not 4, which is the discriminant, which is b squared minus 4ac of a quadratic form. And I'm going to denote by this curly sub t the set of all binary quadratic forms of a fixed discriminant d, and we take them to be positive definite if d is a negative discriminant. And so d can be positive or negative, and if it is negative, whether the question is we're taking positive definite or negative definite, so we're choosing the positive definite ones. So you can also equivalently think of them as the triple of integers with one condition, b squared minus 4ac equals 2. And then that's a standard notation. Instead of writing it as ax squared bxy plus cy squared, we suppress the variables and only write down the coefficients of the quadratic form in this square bracket ABC notation. The group, modular group, just like it acts on the upper half plane, also acts on the set of quadratic forms. And this is the linear action that I was talking about. So if we have an element of the group, A, B, C, D, call it gamma, the new quadratic form, gamma q, will be, again, a quadratic form in the variables x, y, obtained from q by changing the variables x, y to dx minus by and minus cx plus by. There's a reason for this action rather than ax plus by and cx plus dy, is because we want to get what's so-called equivariant action. This is the one that is compatible with the action on the upper half plane. So given any quadratic form, ABC, I can look at the root of the quadratic form a tau squared plus b tau plus c. And then it's a point in the complex plane, and the group can act on this point as well. And these two group actions are compatible. What is known is that this set of representatives for this action, again, whenever you have a group acting on a set, it partitions the set into orbits, and the number of orbits is finite. This is not trivial, but it is not so difficult either. That goes back to Gauss, his famous reduction algorithm, which shows that any given quadratic form of some fixed discriminant d can be put into a certain form, which has conditions on A, B, and C, and that actually shows that there can only be finitely many solutions which satisfy that conditions, and that shows it is finite. And the order, again, is called the class number. And this is the class number in the simplest case of quadratic fields or equivalently quadratic forms. And if we restrict ourselves to so-called primitive quadratic forms, which means A, B, and C are relatively prime, then it actually is a abelian group, and this is exactly the ideal class group in the quadratic field that it corresponds to, which I'm putting under the graph. Here are some examples. So if I take the negative discriminant minus 191, the class number turns out to be 13, and using the reduction algorithm, which I didn't tell you what it is, it can even write down representatives. So these are the 13 representatives. There are now programs on Google, and then you can put your discriminant, and then it will give you the class number and the list of inequivalent forms. And when for the positive we take 28, it has class number 2, so these are the two representatives. So what can we say about the class number? In his famous work, Gauss put forth several statements, conjectures, and articles 303, which is mostly about the negative discriminants, and 304 about the positive discriminants. The first thing he writes down is that the class number goes to infinity as d goes to minus infinity. Gauss's original work actually assumes that d is an even integer, but this can be taken care of rather quickly. So this was what he conjectured first. And then he also conjectured that for any given class number, if you look at all the d's with that class number, that set is finite. And then he also surmises that he gives a list of, for small class numbers, list of d's. For 1, 2, maybe 3, he gives less, even more, because being knowing Gauss, he probably did a lot of calculations. And in particular, nowadays what we call class number 1 problem for imaginary quadratic fields or negative discriminants is that the class number is exactly 1 when it is one of these 9 discriminants. Okay, these conjectures are now proven, and I will try to tell you some history about the proof later. And then in article 304, he also claims that unlike the negative discriminant, actually as for D positive, there are infinitely many D for which class number is 1. And this is completely open. We haven't put a dent into this problem. So this is from a question from 1801 that we still haven't been able to solve. And it's natural to ask, what is the difference between positive and negative discriminants? That makes the positive discriminants so much more difficult. And to me, the underlying reason is the following. Whenever you have a group acting on a set, there's a natural question, and it is to ask, what is this subgroup of stabilizers? How do they look like? So if you take a typical element, a quadratic form, and the so-called isotropic group, or sometimes it is called the group of automorphs of this given quadratic form, which is denoted by gamma sub q, these are all the gammas which fixes that q. And it can be shown that any such element in this subgroup can be put in this form. If Q is ABC, then you can put it in this form, where T and U comes from a solution, positive solution of T squared minus DU squared equals 4. This is the famous Pell equation. So in particular, if D is negative, so this is really sum of two squares equals 4, that doesn't have that many solutions in integers. And in fact, for negative, it's almost always just identity matrix, except for these two special cases, D minus 3 and D minus 4. In that case, it is still finite, of order 3 or 2 respectively. On the other hand, if D is positive, then the group of automorphs, or the isotropy subgroup, is infinite. Infinite cyclic. So, and this is really the main reason, and we will see later that this group wants to play a role when you want to say something about the class number, but it's an infinite group, as opposed to the finite case of negative discriminants. Okay, so this is going, somehow it's jumped, sorry. Okay, so let me start with the easier case of negative discriminant. So given a quadratic form, we said that we can associate to it a point in the upper half plane, which is the root of the equation a tau squared plus b tau plus c. And two equivalent forms correspond to two equivalent points in the upper half plane. So if you can go from q to q prime with an element gamma, then you can go from tau q to tau q prime with the same element gamma. Which means instead of talking about these classes, I can talk about points in the fundamental domain or the action of the group. Instead of looking at over quadratic forms, I can look at over H. Such a point is called a CM point. So for example, the equals minus 4, the class number is 1. There is just one quadratic form, that is x squared plus y squared. So the quadratic form tau squared plus 1 has one root in the upper half plane, that is the I. So that is a CM point. If you increase the discriminant, so for example, about 51,000, then the class number is 273, and you can plot these 273 points in the upper half plane. If you increase, then the class number increases. This is expected. That's what Gauss conjectured, that as minus d goes to infinity, then the class number goes to infinity. So we expect more and more points. And that's how it looks like for even a larger one. So not only that we get infinitely many 4 points, it looks like they actually become dense in this set. In fact, now we know a lot more, and this is a famous theorem of Bill-Duke from 80s that he showed. These points get uniformly distributed in the fundamental domain with respect to the hyperbolic measure. Okay, so of course this theorem also proves Gauss's conjecture, but let me go back in history and say, you know, we actually learned about the truthness of this conjecture way before Bill proved his uniform distribution himself. So Gauss's conjecture again is going, the class number getting large as v goes to minus infinity. The proof has a amusing history. In 1918, Hecke proved that if one assumes the so-called generalized Riemann hypothesis is about the Riemann zeta function, which says that all the non-trivial zeros are on the line real part of s equals 1/2, which is one of the biggest open problems. And generalized Riemann hypothesis is its generalization to similar zeta functions, for example, Dedekind zeta function, which is of course also open. So Hecke, assuming GRH, proved that the class number goes to infinity as d goes to minus. Then, in 1933, it came as a surprise when Doring proved that if Riemann hypothesis is false, then the class number is bigger than 2 for minus d sufficiently large. And a year later, Mordell under Riemann hypothesis and Heilbronn under generalized Riemann hypothesis, they proved that if they are false, then the class number goes to infinity. So, together with Hecke and the theorem of Mordell and Heilbronn, this gives an unconditional proof that the class number goes to infinity as d goes to infinity. Okay, these proofs shows that the class number goes to infinity in an ineffective way. So it does not allow us to solve the so-called Gauss class number 1 problem, which I mentioned that he said that the class number is 1 exactly for these 9 cases. Heilbronn and Linfoot, right after his theorem, proved that actually there are at most 10 such discriminants with class number 1, but they could not exclude this possible 10th discriminant. Then, independently in 60s, so it had to wait about 30 years, Baker and Stark proved that there are exactly 9 such fields. Baker used the method of his method. He developed a method which is applicable to wider class of Diophantine equations, his method of linear forms and logarithms, whereas Stark used this modular method that goes actually back to Hecke. We also have a famous theorem of Siegel, which tells us about the size of the class number. This is a celebrated theorem from 35. He showed that for every epsilon, there is a constant which depends on the epsilon. The problem is that it cannot be effectively computed such that the class number is bigger than c times d to the 1/2. So it grows like square root of d. Of course, a corollary of this is that for a given value, the class number is finite. But it doesn't tell you how to find it because the constant is not effectively computable. So Gauss's class number n problem is the general problem of, we know that for given any n, there are finitely many, but can we give the list of these discriminants? So the class number n problem is really giving this list. And Siegel's theorem, as I said, is ineffective and it doesn't allow us to use it to give a list of these class numbers. Towards that problem, Goldfeld in 1976 made a big step by showing that this problem can be related to existence of a certain L function of an elliptic curve. If that exists, then one can give an effective constant such that class number is bigger than log d to 1 minus epsilon. And Gross and Zagier in 1983 finally showed that such an elliptic curve exists, and this solved the class number problem of Gauss for negative discriminants. So what if the d is positive? This time the root is not point in the upper half plane, but actually on the real line, and there are two roots that are real quadratic irrationalities. And to each non-square discriminant, square discriminants are problematic, they become vertical lines. For any given such ABC of discriminant D, one can actually associate what we call a geodesic in the upper half plane. So that's a semicircle that connects to two roots. And then if you look at the image of this on H mod gamma on the fundamental domain, that leads to what we call the closed geodesic. For positive d, we let epsilon d be this number. This is coming from the solutions of the Pell equation again. And this number does not depend on the quadratic form of the discriminant d. And if we integrate the constant over the closed geodesic with respect to the hyperbolic arc length, then we get log of the epsilon. This is in the context of number fields. Is the epsilon d is the so-called fundamental unit, the unit that generates the group of automorphs, and log epsilon is the regulator. Geometrically, it really measures the length of the closed geodesic with respect to the hyperbolic arc length. So, for example, for d equals 12, when you take the geodesic and project it onto the fundamental domain, you get this closed geodesic. If d is 28, then there are two classes. For each class, you have an associated geodesic. One is staying log, the other is up. And if you increase the discriminant, class number is still 1. So class number is expected to stay 1 for many high discriminants. But the geodesic now, as you can see, covers more and more space in the fundamental domain. And in fact, Duke's theorem has a positive discriminant counterpart which says that as discriminant goes to infinity, the geodesics become uniformly distributed with respect to the hyperbolic measure in the fundamental. This theorem, I've recently seen many reincarnations due to several people, but most notably, actually going back to Linux, using ergodic theoretic methods, Einsiedler, Lindenstrauss, Philippe Michel, and Venkatesh, and many others, reproved Duke's result, whose proof was purely automorphic, and extended them to other settings. Okay, so again, in the case of discriminant D, the uniform distribution of geodesics doesn't say much about the class number. It is more about the geodesics associated to the classes. So the class number 1 problem, in this case, that it is infinitely many D that class number has 1, we said is completely open. What is more, it's not even known that whether there are infinitely many algebraic number fields of any degree that has class number. So instead, in mathematics, if you can't answer one question, you change your question so that you can answer it. So you can ask, can we say something about the total length of the geodesics? And again, we have the counterpart of Ziegel's theorem. Ziegel's theorem was for both of them, that the class number times the geodesic. So remember, for each quadratic form, we have a geodesic. Its length is log epsilon. It is independent of the class. So if you sum over all classes, you get exactly HD log epsilon. You sum the total length of the geodesics corresponding to all classes. And that is bigger than d to the multiplications. And in here, and you will see in a minute later as well, this log epsilon does not want to leave HD alone. And that's exactly where the difficulty is in the class number problem. We cannot get to the class number for positive discriminants by themselves. It wants to come together with the length of the geodesic. Okay, so the next question is there a formula for the class number? Or, since we don't know what it is, for d positive, for class number times log epsilon. And this is a general theme in number theory that tries to relate arithmetic information to an analytic object, which is typically called the L function. Maybe the most famous one of this is Bird-Sivnerton-Dyer conjecture, which is one of the millennium problems, which relates the information about elliptic curves to the analytic properties of an L function or a zeta function that one can associate to the geometric object. But the prime example, this is a conjecture, this is a theorem, is going back to Dirichlet. And Dirichlet proved in, I think it was 1838, that he related the class number, in the case of quadratic forms, to analytic properties, in fact, special values of a certain infinite series, which we now call Dirichlet series. And this is his famous class number formula, which I'm going to say a little bit more in a minute. But it's a very important result because it is the one that really marked one of the most important applications of analytic techniques to algebraic problems. So the class number is a completely algebraic entity, and it relates it to the special value of an analytic object. And this is nowadays a theme that we see all the time. The Bird-Sivnerton-Dyer conjectures of that type. On one side, we have a geometric object and data associated to the geometric object geometrically, algebraically. On the other side of the conjecture, we have analytic properties of an L function that we associate. And there are other conjectures later on that has this theme. But it is really Dirichlet that is credited for laying the foundations of this connection between analysis and number theory, and the whole subfield of analytic number theory. And then later, Dedekind has a class number formula, which again uses his Dedekind zeta function and its special value at 1, s equals 1, to the class number of number fields. So what is Dirichlet's class number formula? It is typically written in terms of a character and so on, but this is a simpler form since I'm using the quadratic forms. It's a sum over ABC, b squared minus 4ac equals d. So these are, you can think of them as over all quadratic forms ABC of discriminant d, with this condition that a positive and b is between 0 and 2a, and 1 over a to the s. So it's an infinite sum, And if you look at it, if you compare it with the harmonic series, clearly at s equals 1, this looks like 1 over a, has no hope of convergence. In fact, it is convergent for a real part of s bigger than 1, and it has a pole at s equals 1. So if we, before I give the formula, if I let the omega minus 3 as 3, omega minus 4 as 2, and omega t as 1, these are exactly the order of the isotropy subgroups in the d-discriminant negative case. Then the class number formula of Dirichlet says that if any fundamental d, it's a technical word, it means it's the discriminant of a quadratic field, but the class number divided by the order of the units is given as the residue, essentially the residue of this infinite sum. So you can view it as like a special value at s equals 1 of the divergent series by going to the residue. And it depends, but this is one of the most beautiful formulas in number theory, as far as I can tell. Okay, there's another class number formula. This is going back to Hurwitz, and it is much less known. Dirichlet's formula is very well known. And it is a formula, in fact, it again gives the class number as a value of an infinite series, but this time it's a convergent series. So it replaces Dirichlet's divergent sum with a convergent sum, with this title that it's a representation of the class number in an infinite series for positive definite quadratic forms. It is much less known, and it is really very surprising that it is not much. Well, once you read the paper, maybe it is not surprising because it's very hard to read paper. It uses projective model of the hyperbolic plane, a lot of projective integrals, and thus things so generally that you lose the main mechanism behind the idea. But the reason I say it is rather surprising that it is not known, because it appeared in 1905 in a very good journal, Krelle's journal, and it is a special volume for Dirichlet. And it's a really humbling experience to look at the list of contributors of this volume. Dedekind, Frobenius, Ansel, Hilbert, Hurwitz, Mertens, Minkowski, Miranov, Picard, Poincaré. So I think this whole volume should be read again and again. Okay, and here is Hurwitz's formula. It looks similar to Dirichlet's. On the left, we have the class number divided by the order of the unit group, and d to the treehouse, some highs, and then it's an infinite sum, 1 over a, c, a plus b plus c. So you can see that it has order like 3 as opposed to 1 over a in Dirichlet's formula. So this one actually converges, each sum is positive, and in fact it converges, it increases monotonically to the class number. And he gave classes of other formulas that the rate of convergence increases. This is the simplest one. And the formulas for Hurwitz is for fundamental d, but it's actually for any negative discriminant. If you replace class number divided by the unit group by the Hurwitz class number, that is now what we call Hurwitz class number, because it's a very natural counting of the orbits. Instead of counting each orbit by 1, we count each orbit by the, we normalize it with the length of the stabilizer. So we weigh each orbit with the order of the stabilizer. So in that sense, it is also a natural count. And if it is fundamental, what appears on the left, which is class number divided by the order of the stabilizer group, is simply the Hurwitz class number. So both Dirichlet's formula and actually Hurwitz's formula is for the Hurwitz class number. Is this going back? Okay. So, now for the positive discriminant, Dirichlet actually gave both results for negative and positive. Let me go back to negative quickly. Here we have class number and the order of the stabilizer in terms of the residue of this series. This formula for the positive one is exactly like this. Again, the same series, but again the residue. But on the left, we have the class number, this time weighted by the length of the geodesic corresponding to each class. Okay. And the natural question is whether there's an analog of Hurwitz's formula for the positive. And this is, he didn't do that, but it was possible to give a generalization of Hurwitz's formula for positive discriminant as well. And this is one theorem that I will mention, which is due to Bill Duke, myself, and Arpad Claude. And the same ideas that is hidden in Hurwitz can be used to give a formula in the case of the positive discriminants. And as with anything else, positive discriminants are more complicated, but it is of the same type. These are rational functions in ABC. There is an infinite part and there is a finite part. So it has two parts in this. And again, it converges monotonically to the actual graph. And recently we have actually tried to understand Hurwitz's paper better, and once we understand paper better, we can see that his ideas can be put into a general context, and then this general context can be applied to many other problems. In particular, it gives formulas for class numbers of not just binary quadratic forms, but ternary, quaternary, quadratic forms. The formulas get more and more complicated. It also can be applied to give formulas for class numbers of what is called permission forms. These are really an analog of quadratic forms, but in the case that PSL2C, not R, is the underlying group. And then if you use some invariant theory, then one can actually prove a binary cubic, not quadratic, but cubic formula for the class number. And as far as I know, this is the first case of such a one. So, how am I doing with time?
You have 5 minutes.
Okay, so if I have 5 minutes, since I said Hurwitz's result is not known, and I think it deserves to be known, I just want to give a very brief idea of his, the idea behind Hurwitz's paper. So, because that idea can, I believe, can be applied to other problems. And the idea is the following. You have a group and you have a set. I call the group gamma, I call the set X. It acts on the set. My assumption is that it acts with finite linear orbits. And the second assumption is that the stabilizers are all finite. For example, the real quadratic case doesn't fit into here, but I'm giving you the simplified version. Okay, so assume that I have such a group acting on a set with finite linear orbits, finite linear stabilizers. Assume that I was so lucky that I found a function, rho, and I call this function partition of unity, or leading to a partition of unity, so that if I take this function and I pick arbitrary point and look at this function over the orbit of that point, so I'm averaging over that orbit. And it's a magic function in the sense that it is always 1 no matter which point you choose in X. So this is at the heart. It's not always easy to find this function, but assume you found this function. Then, instead of summing over the group, now I'm taking the same function but summing over the set. The set can be divided into finitely many orbits. So I can sum it in the orbits. Then if you teach a course in algebra and group actions, the first thing we teach, or one of the first things we teach, is orbit stabilizer theorem, which says that I can rewrite this. I have to weigh with respect to the size of the orbits and then sum over the orbit of the representative. But this one here is just like that one. It does not care about xj. It is 1. So I get that. And that's exactly the Hurwitz type number. And that is the idea of that is B. So if you take, for example, X as the quadratic set of quadratic forms, the group as PSL2C, then we still need to find this magic function. And Hurwitz uses projective integrals to write these magic function. We used, in the case of SL2C, some spectral theory and point pair invariance to construct this function, and we show that that's such a function. That leads to a partition of unity, and hence it gives the class number of Hurwitz. So I'm going to stop.
Thank you very much. It was a very interesting talk. Any questions or remarks?
Hi, thanks. When you talked about a constant that cannot be effectively computed, this is Siegel, I think.
No, Siegel theorem.
Is that part of the theorem, or just that the proof didn't provide a way to compute it?
Proof didn't, yeah, it is certainly.
Okay, I mean.
Yeah, because later there's a different bound, which is the Goldfeld, sorry, I go back. That constant. So Goldfeld has shown that actually you can give this bound. Sorry. It must be a better, I passed it. Here. So here, this C can be effective.
I mean, it was a non-constructive.
Non-constructive, exactly. It gives you the correct bound, but it doesn't tell you what that constant is, and once you don't know, you can't list the fields.
There are these two Duke proofs for the convergence to uniform distribution, something like that.
There are many.
Minus 20, or minus and positive.
No.
Are there any sort of understanding of qualitative differences between these two convergence processes?
Okay, so actually the proof of Bill is not different, it's the same. It's just that it tells you that the quadratic fields, or the quadratic forms, has a geometry. For the negative discriminant, they correspond to points, and for positive discriminants, they correspond to geodesics. Actually, recently we have shown that there's a third geometric thing, a surface associated to quadratic fields, which is actually a Riemann surface, which is bound by the geodesic. So in some sense, the positive discriminant's geometry is more complicated. The method here is purely automorphic in Bill's case, and it gives both cases. In fact, what it does, it constructs the sum as a Fourier coefficient of some automorphic form. Then it is known that these coefficients, this is due to Ibanez, it's this famous theorem, that these coefficients, this is called the Weil sum, and the analog of that is summing this test function over the CM points. And these Weyl sums in both cases corresponds to positive or negative coefficients of some mass form. And we know that they're small. Small compared to the discriminant, so that this converges to this. So it is a very automorphic and maybe you can say representation theoretic proof. And then the proofs of Einsiedler, Lindenstrauss, this is very ergodic theory. They're not effective either. So I think what we can access with this theorem is the geometry. It comes with this log epsilon.
Any other questions, remarks, comments? Okay, let's thank our speaker again.